To have Simon Benjamin from the University of Oxford. Is the quant, is in the. Is that right? You're in the material department.
That's right. Yeah, I'm actually in the materials department. A lot of people assume physics, but in Oxford, we're very spread out over the departments, the quantum crew.
Right, and he's a really leader in quantum computing, and he was leader, one of the leader of the UK National Quantum Computing Center, National Hub. He has a big group working on various topics from algorithms, fault tolerance, error correction. He did some amazing work on NISQ quantum computers. And today we'll see. You'll tell us whether they can work or not, I guess, right?
Yes.
So Simon, the floor is yours. Thanks.
Well, thank you very much. And I'm not sure if this will interfere with the protocol you're planning on, but I'm very happy to take questions at any point. I think it's actually a little bit draining to just talk for 50 minutes with no feedback. So please do interrupt at any point, and maybe I'll remember to pause here and there to invite questions.
Right. So you can unmute yourselves and ask questions if anybody's interested, or you can send a question in the chat.
Brilliant. I won't necessarily see the chat, but perhaps you will.
I'll be monitoring it.
All right. So here's a picture of my group, not really up to date, but it has some of the faces of people who I will mention in this talk. Let me bring up the names. So this was back in the days when we were all allowed to socialize in a large group, which currently in the UK is not allowed. We would have to cut that off at 6 people, sadly. But yeah, so in those halcyon days, our group being photographed in the park. And particularly Sai and Balint, who are on my left and my right in this photo, are two people who you may notice their names coming up as I talk through some of the group's recent outputs. But all of the people mentioned here have been involved in the work I'm going to talk about. So let me sort of set the scene a little bit. Why does NISQ matter? Why do we even phrase the question if I come back to my title slide? So I'm asking quantum algorithms and architectures for the NISQ era, the noisy intermediate scale quantum era, can they really work? I expect you're guessing that I'm going to say, yes, they can really work. It's all good. Well, maybe I will, maybe I won't. You'll have to wait and see. But why are we even asking that question? So let's have a little look. What's the world's biggest quantum computer? Well, many would answer that question by pointing to Google's very beautiful so-called supremacy result from last year. This was a chip with 53 active qubits on it in a nearest neighbor layout, as shown in the schematic there. And depending on whose analysis you follow, replicating the output of that machine, which was essentially a benchmarking task that wasn't inherently useful, but which did display its quantum nature, replicating the output with classical supercomputers would take something between days and many hundreds of years with the world's most powerful current conventional computer. The debate as to whether it is days or many hundreds of years is really irrelevant because it's an exponentially scaling thing. So as others have pointed out, it's a little bit like when a chess computer defeats the world champion, but the world champion manages to score one game of it, or in Go, you're an inflection point, and in a year's time, it's going to be 100%. So we are entering the era when we can try and do interesting things because our quantum devices fundamentally outperform, or rather enter a domain where they can't be simulated by classical machines. But 53 qubits is the number, and that's impressive. But for fault-tolerant quantum information processing, we may need millions, in fact, perhaps billions of physical qubits. And so what would that take? 53, very, very, very beautiful achievement, but how could we close that enormous gap? So one way to answer that is to look at a blog post from Jay, who's a leader on the IBM side, a very interesting blog post that went live just a couple of days ago, showing IBM's roadmap towards scaling up quantum technology. And they have a very ambitious roadmap, which suggests over 1,000 qubits by the end of 2023. So I suppose over 1,000 qubits in 3 years. And that does seem to me to be an ambitious, exciting roadmap. And an interesting part in that, I'd encourage you, if you just Google IBM roadmap, it will probably be the top hit. The interesting read. And one of the things that Jay tells us is that they are also working on a mega deal fridge. 10-foot tall and 6-foot wide super fridge, internally codenamed GoldenEye for some reason. And that's a beast of a deal fridge that's designed to be able to cool a system with perhaps up to an order of 1 million superconducting qubits. But 1 million superconducting qubits is still not likely to be enough to do really interesting tasks in the fault-tolerant era using the codes that we understand the best, things like the surface code. There we would expect there to be something like a factor of 1,000 between the physical qubits and the logical qubits, which are now almost perfectly error-free. And so then your 1 million qubit device just becomes 1,000 logical qubits that the programmer understands. And that not many things fit in there. Some interesting things certainly will. But if you look at, for example, famously, Shor's algorithm is something quantum computers should be able to do. And that is not one of the ones, that's one of the relatively friendly ones in terms of the qubit count. And there you're looking at several thousand qubits. You need certainly as many qubits as it takes to represent the key that you're searching for, the factor. And so that's, say, 2,000 to make it post-classical. And then overhead factors would take you up by some modest factor. So
can I ask a question? I'm sorry,
please.
Since you invited.
Yeah.
So I would like to know, where is the number 1,000 coming from as the ratio between logical and physical qubit?
Yeah,
what's
absolutely.
Yeah.
Well, I will come back to that a little bit later, but let me briefly answer. So that comes from choosing, you need to choose a particular code you're going to use, a particular approach for fault tolerance. So if you look at the surface code, which has many merits, and in fact, even the code, IBM currently favor a slightly different code, but it's very much in the same spirit as the surface code, then what you can do is figure out, if you put in a physical error rate, and then you give yourself a certain number of physical qubits that encodes each logical qubit. So this is a code where essentially a block of physical qubits is dedicated to just one logical qubit, and there are other approaches where you would sort of get n into m. But in this case, you can figure out what kind of error rate you're going to get as your logical error rate as for a given physical error rate. Now, of course, if that physical error rate is too high, if it's above the threshold of the code, it won't work at all. But once you go below the threshold, you now are in the regime where with sufficient physical qubits, you can get whatever target logical error rate you want. Of course, you will never totally eliminate errors, but your game would be, in something like Shor's algorithm, you would work out how deep the algorithm is, how many gates have to happen to the logical qubits, and you would say, I want an error rate, a logical error rate, such that I will not have a single error occurring in my entire algorithm. Probably, whatever you want, 90% chance that you don't get an error anywhere in your algorithm, and so that the output is meaningful. So that tells you your logical error rate, and then you figure out, given your physical error rate, what size you need to be at. So in the example I gave, I know of a couple of papers that take a physical error rate around about 0.1%. So you can think that one time in 1,000, when you try to do a gate operation, sort of some random junk happens instead of the ideal gate operation. That's tough, but has been achieved in some systems. So that's a reasonable assumption for your physical error rate. And then you take Shor's algorithm and work what logical error rate you would tolerate. And then you look at essentially how the error rate scales as the code increases. And you end up with a 30 by 30-ish grid of physical qubits is what you need to accomplish the extremely low logical error rates, say 10 to the minus 15, that you might want for your application. There's lots more to say about that, of course, and one, I won't get into it, but one remark that's worth making is that these things are very sensitive to the exact nature of the noise. And these rather surprisingly, difficult numbers, this 1 to 1,000 ratio, presumes noise that is a sort of a white noise. It affects all different noise channels equally. And things may be better than that in reality. If the noise is focused into one channel, one degree of freedom, that's actually good news because you can fight it more effectively. But I'll actually come back to this a little bit later on. So for now, maybe I'll just push on. Jay tells us that the team is developing a giant deal fridge, which can perhaps host a chip with 1 million qubits. But being aware that 1 million qubits is really not enough to be a universal sort of general purpose fault-tolerant quantum computer that can tackle the full range of things that we hope for, such as solving chemistry problems, maybe some machine learning stuff. He also notes that they're working on linking up, or they anticipate linking up these mega deal fridges with one another, much as in a conventional computer center, you see the boxes are linked up with an intranet. And so you're ultimately looking for your single quantum computer. You're looking at a facility which may have dozens or hundreds of these mega deal fridges all connected up. So a very large, commitment, which is fine, but it shows you that this is a very, very interesting and substantial challenge. And that motivates NISC, coming back to my point, because if that's what needs to be done, and maybe it is, maybe it isn't, I'll return to this at the end of my talk. If that is what needs to be done to achieve the fault-tolerant machine with a meaningful number of logical qubits, then it's not going to happen next year. We need to be thinking about, can we get value out of much more modest systems? So in other words, here we are with a number of groups can do 20 qubits, one group can do 50 qubits. We need to get into the millions of qubits at least to do interesting tasks. And we need things that are going to generate value and show that we're on the path in order to sort of have the investment to build across that chasm, I think. So things in this talk then, I'm going to talk mainly about variational quantum algorithms, so QVAs, quantum variational algorithms for NISC, which is I would say, the big hope for getting value out of near-term noisy systems. That will lead us to think about gradient descent, in other words, how you configure your machine, and also a thing called error mitigation, which is a sort of poor man's fault tolerance, which doesn't cost extra qubits, but does cost us in other ways and doesn't perform as well as full quantum error correction. And then with those sort of ingredients, we can ask ourselves, well, is it actually going to work? Actually, I see that I've decided to spell it one time as quantum variational algorithm and another time as variational quantum algorithm. Excuse me for that. But in either way around, do these approaches really work? Can we expect to get meaningful achievements, things that could not have been done by other means and that are valuable out of these NISC systems? And then a quick interlude. I'll just tell those who are interested something about the tools we use in our studies, a system called Quest. And then I'll wrap up by coming back to this sort of eventual goal of fault-tolerant QIP and sort of try and contrast its pros and cons. So here is the quantum variational algorithm schematically. The idea is that we have a number of qubits that is enough that it is practically impossible to simulate with a conventional computer, so let's say more than 50, but we don't have enough qubits that we can start saying, excuse me? Or perhaps someone didn't intentionally speak there, so I'll carry on. And then we have a circuit which is composed of a whole bunch of quantum gates, of course, single qubit gates, 2 qubit gates, let's say. But the thing is that each one of these gates is not a single fixed operation, but rather it's a family of different things that we could do on a particular run of the circuit. We have a parameter, an angle, that we can think of it as an angle associated with each of these operations. And we might say that when that angle is set to 0, then the gate is just the identity. It doesn't do anything. But if we switch the angle to, let's say, 90 degrees, then our gate is in full force. And so this Z rotation that's highlighted in the sketch might be a full Pauli Z flip in that case. But we can freely vary that parameter in between and continuously change the operation so that, in fact, we aren't looking at a single quantum circuit here. We're looking at a family of quantum circuits indexed by that list of parameters, a different one for each one of our gates. So this circuit could be anything from if you set all the angles to 0, it's just the identity and doesn't do anything, through to a very rich range of different processes that could be performed by this quantum circuit. And the question we ask is, if we have some particular task in mind, is there some set of angles, some set of parameters for which this circuit will perform that task for us? And if so, how could we find those angles in an automatic way? We hope that, well, we will consider circuits that are not very deep, in other words, not very wide in this diagram, right to left. And that's because we assume that noise is happening every time we perform an operation, and even in the times between operations. And so if we try a very, very deep algorithm, what we're likely to get out at the end is just an extremely mixed state, just junk. So we try and keep the algorithm as shallow as we can and hope that there is enough power there to perform a task of interest. That's roughly the gist of it. Now, my group's work in this area has, much of it has been around the story of a particular matrix, and I think that's a nice way to introduce some of the ideas. So that's how I'm going to set out the next few slides. We first encountered this when we were thinking about the question of how to do quantum dynamics with a system like this. And what does that mean? Well, and I apologize that the sort of font style jumps around a bit over these slides. What we ask is, how can we update the parameters in our circuit step by step, making a small change each time, such that as we look at the output from our circuit, it represents the evolution of an interesting quantum system. So you could imagine, for example, a network of spins, and you want to understand their dynamics. You start them off, for the sake of argument, in a simple state where each spin is definitely up or down. And that is the state that you feed into the network. And the output from the circuit should give you the state of that spin register at some later time t. And if you can achieve that, then the next challenge is to figure out how to update the parameters in your circuit so that now it generates the state of the system at time t plus delta t. So you're incrementally tracking the dynamics of a system. Modeling the dynamics of interesting quantum systems, whether they be spin networks or molecules and so on, is one of the things we hope quantum computers can do for us. If we had a universal fault-tolerant machine, there's a range of techniques we could use, but we were asking, can we do that kind of thing with NISQ? So just to sort of set that problem up, what we want is to track the Schrodinger equation for the system. We'll assume it's a closed system. For simplicity, it doesn't have to be. And what we've got here, instead of the general solution to the Schrodinger equation, is we've got the output of our circuit, which depends on parameters, which themselves depend on time. And we want to know, given that we have them configured some way, and the output of the circuit now represents the state of the system at some time t, how should we now update the parameters, just these classical numbers? So we go around some kind of cycle involving studying our quantum device, making some measurements, feeding that into a classical algorithm that might do some non-trivial stuff, and then works out how to update the parameters. And so what we'll do here is, what we do is just a variational principle will do it for us. This is a McLaughlin variational principle approach that we take. So we just take the Schrodinger equation and we say, well, if the Schrodinger equation is satisfied, then that left-hand side, moving both terms to the left, that should be 0. And so if we think of the length of that vector, it should be 0. It may not be possible for it to be 0 because, of course, our circuit may not be complex enough to actually track the dynamics perfectly. So what we should ask for is that as we change the parameters, that distance stays minimal. So we minimize that. If we take that principle through, and I'll show you some references later where you can follow that process through, we end up with the following. In order to update our parameters the way we would like to, we end up having to solve on our classical computer a piece of linear algebra, an equation like this. The thing we're after, the way that we should update our parameters, is the solution to this equation where we have a matrix and a vector object. And these things, the terms in that matrix and in that vector, need to be populated by studying the quantum circuit in its current configuration. So we run it again and again and again to figure out the numbers in this vector and this matrix, and then we solve on the classical computer and update. And what are these two things? Well, here they are defined formally, but I think on the next slide I say a bit more about that. So the vector object is not so strange. In fact, its real part is just the energy gradient. So if we imagine that our Hamiltonian has some value for each possible setting of our parameters, then the real part of that vector object is just the gradient now. We'll see more about that in a moment. But what about this matrix? This matrix is an intriguing thing that we just came up with as a part of our analysis, and we didn't really obtain a very deep intuition about it, but we argued that it can be measured efficiently with our quantum circuit, and that if indeed you follow through the protocol I've just described, then it does work. We showed that you successfully can track the dynamics of a quantum system that you're interested in using your quantum computer. And what we've got, what this matrix is each term is the inner product between the way that the output state changes with one of the parameters and the way the output state changes with another one of the parameters. So, you know, it's interesting to muse about what that is trying to tell us, and I can say more about that using insights that came from a different group in a moment. All of this, though, when we first encountered that beast, it was 2016, and we wrote a paper about matching about quantum simulators on that principle. But if you were interested in this kind of thing, I would actually refer to you to this more recent publication, which has a more comprehensive analysis, and in particular notices a problem with global phase and how to accommodate that, which we missed in the first paper. So now, back in 2016-17, we were chatting with a team of theorists from IBM, including Kristen and Sergey here, and they had a very interesting suggestion for us. When we talked through how we model the dynamics of a system, Sergey said, you should try it with imaginary time and see if it makes a nice eigensolver. And let me tell you what those words mean. First, a reminder about eigensolvers. So this is actually the most common thing that people discuss trying to do with a variational circuit. Here's a little toy variational circuit, a very trivial one that only has 2 gates and 2 parameters. And over here is a Hamiltonian. And this Hamiltonian, of course, we can see the properties of by eye. It's very trivial, and we can see that the ground state is going to be the 1, 1. If we imagine it's a 2 qubit, so 0, 0, 0, 1, 1, 0, 1, 1, then the ground state is 1, 1 and has energy 0. So we can see that by eye, but what would happen if we tried to solve that systematically using variational techniques? So we would have our rule about how to update things, but now because we are trying to not model the dynamics but find the ground state, we would update our parameters by finding the direction in which the energy landscape was going down most steeply and go in that direction. And what that would lead us to, for example, is if we started up here, it would take us down here to the solution. But notoriously, these kind of optimization problems are non-trivial, and even this very, very simple example exposes a problem, which is if, depending on where you start, you don't necessarily make it to the ground state by following that steepest descent principle. In this case, it's so trivial that you can sort of imagine adjusting your rules to overcome it, but it already exposes the problem. We can get stuck in this trench, which has no gradient, rather than reaching the minimum. So that is an example, a toy example of an eigensolver problem, which also exhibits the problem with such things. And what Sergey was suggesting to us is that a different rule that you could use for solving those kind of problems is to appeal to an imaginary time evolution instead of going down the steepest gradient at any moment. And so what would that look like? This is an equation that shows you what imaginary time evolution really means. It looks a lot like a Schrodinger type evolution, except instead of IT here, we have tau. That's why it's called imaginary time. This is clearly a non-unitary evolution because this operator is going to attenuate the state. And if we imagine this state being written out in the eigenbasis, it's going to attenuate the high energy terms more than it attenuates the low energy terms. And if we imagine that we're constantly renormalizing, then we can see that the eventual convergence, or the steady state here, is to have attenuated all states except the ground state away. So it's a way of finding the ground state, and that's used in classical techniques. It's not so hard to repeat the stuff we've done for quantum dynamics with this new idea in mind that Sergey suggested. You end up with the same kind of principle, a variational principle that just looks slightly adjusted, and you follow that through. And then what we end up with the following. When we, instead of doing a simple gradient descent, you do a modified gradient descent where you still need to work out the vector that represents going straight downhill in terms of energy, but now you need to apply a matrix to that, to adjust that direction. And what is that matrix? Well, it's the same thing that we previously encountered, unsurprisingly. It's a similar derivation. Again, this thing here is the crucial element. And by the way, let me just mention at this point, you might wonder how on earth does an experimentalist measure this? Well, it's not so bad. There's a range of methods, but a rather elegant one is this. You just apply your circuit, you apply an extra operation in the vicinity of gate 1 and of gate 2, conditioned by an additional qubit, or controlled, I should say, by an additional qubit. And so this is a swap test type structure for those who are familiar with these things. And you simply measure the ancillary qubit. You don't actually care about all the other qubits in this approach after you've finished applying the circuit. And the measurement that you obtain here tells you this inner product, essentially. So a fairly straightforward thing to do in the laboratory, costs you 1 extra qubit. It's cheaper to measure than you might imagine. So returning to our toy model, what does that do for us? Here was the basic gradient descent that had been much studied by many people since 2015 or so. And here's what happens if we try Sergei's suggestion. We get a different evolution. We no longer go down the steepest gradient. We work out the steepest gradient and then adjust it with that matrix. And in this particular model, that has the pleasing consequence that you always find the ground state. Unfortunately, you don't always find the ground state in more complex problems. But again and again, we found, when we tried it on problems of interest, that this new imaginary time descent mechanism outperforms the canonical gradient descent. And I can offer in a moment an insight as to why, but still I must say, within our group, we didn't really entirely grasp why that was happening, but we observed that it did. Here's an example of a paper that sort of looked at that in a more concrete, less of a toy model, although still very, very small. It's an 8-qubit problem. 8 qubits are sufficient to represent in a certain way the lithium hydride molecule and to look for the energy of its ground state. And these lines here represent how well you do if you use canonical gradient descent versus this new idea of imaginary time. And so, for example, with the dashed lines, lower is better, and you can see you get nearer to the ideal solution and more rapidly. You get there more quickly. So we were interested by it.
Can I make a quick remark?
Please.
I'd just like to say that this is actually, it looks like an algorithm which is known in classical algorithms, variational Monte Carlo algorithms, which is called stochastic reconfiguration, where it's also known that essentially a variational way of doing this kind of algorithm outperforms usually gradient descent.
Yeah, well, that wouldn't surprise me. If you hold your horses, then you'll see that on the next slide, I'm making a very similar remark, although that came to us from another group. But so you will be able to tell me if the next couple of slides are in line with your remark. So, but let me first just summarize. So if we use our quantum device to obtain these key objects, a certain, essentially a gradient and a matrix, then we have access to regular gradient descent. That's if we ignore the matrix. We can do an enhanced gradient descent using the matrix, although the inversion, of course, may be non-trivial and must be done on the classical machine. And we can even, by taking the imaginary rather than the real part, we can have the Schrödinger evolution of the dynamics. So it's a rich object, but what's the intuition behind it? And so the answer to that came from a group under James Stokes, and they observed that what was going on here was the quantum generalization of natural gradient. So natural gradient is a technique that some of the authors of this paper were very familiar with from conventional machine learning and optimization. And roughly speaking, the matrix A, so when we now put it in the quantum format, reconciles the parameter space to the problem space. So we can see that, let me see what's on my next slide. Yeah, okay, it's good. So the reason that it does this nice job for us, one way to see it intuitively, is that over here, when we just naively descend through the parameter space, sometimes when we change a parameter a lot, it's actually not changing the output at all, which is why, in this case, we get these flat trenches. So in parameter space, we think we're moving a great deal, but in fact, in Hilbert space, we're not moving at all. And the use of the natural gradient method reconciles between our parameterization of the problem. The problem for us is, getting to a point in Hilbert space, and the nature and the solution itself, which is that point in Hilbert space. So by correcting, we understand then that sort of as you approach this trench, let's say, you need to change that parameter a great deal if you want to move a little distance in Hilbert space. And so that gives us these, in places, radically changed trajectories. So let me pause there and ask whether that was along the same lines that the questioner was thinking or not.
So this is I would say the machine learning language for this, right? Natural gradient is what the machine learning people would call it. But the chemistry algorithm dates back about 15 years. And that is called stochastic reconfiguration. I think this is exactly the same thing mathematically, but just calling it a new algorithm, I think, is a bit.
Oh no, absolutely. I wouldn't suggest that the quantum people, whether it be James's team or my team, had invented a new algorithm here. In fact, much of the work in the NISQ era especially is really the adaptation of existing ideas, or sometimes the rediscovery of existing ideas, just because the people on the various quantum teams, don't have the expertise of people from, say, quantum chemistry backgrounds or from machine learning backgrounds. So in this case, I would say that we came across an approach by thinking first about dynamics and then about imaginary time. And of course, imaginary time itself is a technique that's widely used has been widely used in classical analysis of many body problems, quantum chemistry, and so on. So we're well aware that this is, these were ideas being adapted into the realm of having an actual quantum coprocessor from things that were studied elsewhere. But what we didn't know, I mean, what I certainly didn't know, was that this particular one goes by the name of natural gradient and is studied under that heading in the machine learning literature. But so I mean, it was an interesting joining up of dots for me, and it was really nice to then be able to have a look at that literature and see what people had to say about it on the classical side. But absolutely, practically speaking, it presents a superior way of trying to solve variational algorithms at the cost of doing a bit more sampling. And I could say more about that cost, but it's not as much as you might think when you note that there's a matrix that you now need to evaluate as well as a vector. It's essentially a cost that becomes not the primary cost as the system scales. And so essentially you should use, my remark would be, you should use quantum natural gradient over canonical gradient descent according to all the stuff that we've seen. So, we were very interested to see that, and let me skip through this slide. Well, okay, so on this slide, it's just some remarks about references that can talk about simulating very general processes, and what would we get if we take these ideas, and remembering that this is supposed to be in the NISQ era, if we accommodate noise, not just by saying, well, this is how it would work perfectly, let's hope it still works well when we have noise in our gates. Instead, if we generalize our gate objects away from being unitaries to non-unitary processes, what kind of dynamics do we then get? So it's possible to quite formally derive the correct update equations for arbitrary non-unitary elements rather than just unitary gates, and that gives this paper here, quantum natural gradient generalized to non-unitary circuits, which also has a rather nice performance when the nature of your operations is can be sort of, you are able to formally describe what they are as non-unitaries. Then you can incorporate that into the gradient descent process itself very completely. So before we move on, two things that I want to mention before changing the sort of theme a little bit. First, just for those who may be interested, the fact that you're in these approaches running your quantum computer over and over and over again, or essentially changing the parameters each time, allows you to do some things which are specific to that approach. One here is, how would you go about finding the entire low-lying spectrum of some problem system of interest, like a molecule? An approach you can take is, in fact, to try and find one of the low-lying states by gradient descent, and then modify the Hamiltonian, which in fact leads to just a modification of the way the parameters are updated in a very natural and efficient way, to ban that particular state. Effectively, you rerun the problem with a new Hamiltonian, for which that state you've already found now has a big penalty energy associated with it, so it won't be found a second time. And you can repeat this process without the search process becoming significantly inefficient multiple times until you've mapped out the low-lying spectrum of your system. The comparison on the left and the right here is just the difference between using natural gradient, as we now think of it, in other words, imaginary time, where the process essentially works near perfectly, versus using canonical gradient descent, which often gets stuck in false minima and leads to you mapping out a sort of semi-fictional low-lying spectrum.
Simon, if you punish specific eigenstate, doesn't that lead to a very kind of non-local Hamiltonian?
Well, yes, exactly it would, except that you find that you can punish that state in the way that you are treating the parameter update, rather than, so you don't start by a Hamiltonian that sort of tries to, you don't sort of formally write it as the old Hamiltonian plus some big constant times a projector onto the bad state. That would be a complex Hamiltonian to try and implement. You can do the same thing effectively by altering the rules in which you update the parameters. So that's the observation. And I take a look at this paper if you're interested in the trick there. But exactly as you say, if it were not possible to do that, if it were not possible to accommodate it essentially inside the classical update rule, it could become very inefficient way to search for states. But I really want to, of course, I'm always open to questions, but I would like to whiz through a few things quickly now, because I want to get to a juicy bit at the end. And I kind of want to just give a sort of a whistle-stop tour of some interesting observations. And in particular, I would like to talk about this thing, which is, we stuck on the archive just last week or so, which we call quantum analytic descent. And so this is an exploitation of the fact that given that we have a standard unitary ansatz circuit, so leaving aside for a moment the generalizations to non-unitary noise burden gates, we know that the cost function must have a very simple form. In fact, if you freeze all the parameters, so the cost function is just the energy, the expected energy of the output state with respect to some Hamiltonian. And if you freeze all the parameters but one, and then then sweep that parameter, you should see a sinusoidal type oscillation in the output. This is an observation that a few people have made in the last couple of years. And you could use that as your gradient descent mechanism, in that you could freeze and unfreeze the parameters one at a time and sort of find the minimum of the sinusoidal, that one is on, and then go on. But that still leads to a rather long gradient descent process. So the idea that my postdoc Balint came up with was to say, well, why don't we, so sorry for all the text on this, once we're in the vicinity of a minimum, so there's a bunch of ways that you can see that you're starting to reach a minimum, but it's often the very costly part of these processes is to exactly reach the minimum or exactly to your satisfaction. And so you're somewhere on the slope here, and what you do is you do an extra bit of sampling that is intended to be able to fit the entire analytic function that describes the cost function just by probing around at the point you're at. So over here on the right, we see a sort of illustration of this. The gray lines represent the contours of the real cost function, and the dashed lines represent the contours of the analytic function that you have fitted to that, with actually a relatively modest amount of probing around the point that you're at. And then having come up with that analytic function, so rather than just a gradient, you're now proposing an entire functional fit. You can now, in your classical computer, try and descend to the ground state. So the quantum computer is offline for a bit. You just solve the problem of, by whatever means you want to try and use, of getting to the minimum of this function. And then you, so essentially from the quantum processor's point of view, all the parameters take a very substantial update, not an incremental update as is usual in gradient descent, but rather a jump to what you hope is now very close to the ground state. And then you sample again, and you can repeat the entire process. You can again improve the fit of your analytic function if you're not satisfied with how close you've come.
Is it really, do you need really to fit to a sinusoidal function, or is it enough to fit it to a quadratic form?
You could fit to other forms, but Balint found that fitting to a essentially a trigonometric expansion, which has products of parameters, so it's sort of it's a substantial expansion that has a number of terms. A lot of them are essentially zero or near zero, but has a number of terms that goes with the square of the number of parameters. gives you an excellent performance. I mean, it's a first paper. We haven't, you know, there may be other ways of fitting that are more efficient and maybe other remarks to make. But let me show you this. So this is from simulating a 12-spin ring Hamiltonian, which is a classically hard problem once you have enough spins. And the dashed lines were our previous favorite thing, which was a natural gradient descent. And this is the number of iterations it takes to get to within a certain energy of the ground state. And unsurprisingly, perhaps, when we take this approach, we start off using essentially the same kind of method. So it starts off the same, but then we switch over to this analytic mechanism and we zoom down extremely rapidly to the desired precision. That's because each one of our steps is now the result of a bit of heavy analysis on the classical machine. And of course, we should ask, is that actually a thing that scales practically on the classical machine? Are we doing so much work classically that if we tried it for a 100 qubit problem, it wouldn't be tenable? So Balint spent some time optimizing the classical approach, and he found in the particular approach he was taking that essentially it is the runtime on a laptop, in this case, is just cubic in the number of parameters, which is okay, because your number of parameters will not be vast. You won't be dealing with millions of parameters for any kind of problem that's relevant to NISQ. So we anticipate that with a, you know, meaty but not particularly special classical machine, we can do the work we need to do. So essentially what we're doing here is moving more of the work into the classical machine, where we can access, you know, relatively cheap, amazing hardware, and away from the quantum device to reduce the number of times we actually have to execute the circuits. So that I think is quite an interesting idea, and we've got some interesting feedback from people from our preprint. Now I would like to say, for just 5 minutes, I think, so I may skip through a few slides, a bit about error mitigation. I sold this as the poor man's fault tolerance, and it is, but it's very important to understand its limits, because it's the only kind of error handling that we know is relevant to the NISQ era. So I remind you that with our hybrid algorithms, so the quantum variational algorithm is in the class that would be called a hybrid algorithm, because it is using a bunch of classical resources as well as the quantum coprocessor, which you try and use only in bursts, in other words, for shallow algorithms. We're finding in these kinds of algorithms, we're typically finding the expected value of a qubit or a set of qubits as the output from our quantum machine. And this is an important point. So what I mean here is that if you run Shor's algorithm on a full universal fault-tolerant machine, the output is actually the binary representation of the solution, or more generally of some function of the solution. You still have a bit of work to do, but the output is a binary object. Or in Grover's search algorithm, you're looking for the solution to a problem, and when you finish the algorithm and you measure, it is simply the binary number that solves the task, the problem. On the contrary, with these hybrid algorithms, we are typically looking for the expected value of a qubit or set of qubits with each run of our circuit, or each configuration of our circuit. So that even with a perfect device, we would have to run a bunch of times in order to get that expected value, because each time we're either going to measure a 0 or a 1 on that qubit or set of qubits. Now that leads us to some options for handling errors that we might not think of if we were thinking in the more traditional model of just, you know, the answer is some binary number that is the solution. So we're going to repeat our circuit many times, even with the same set of configurations. And how can we exploit that to reduce noise? Well, I'll mention a couple of routes very briefly. It's a big field, and I do want to get to the last part of my talk, but it's really, I think, essential to spend a bit of time on this. The first trick that you might use, given that you're going to repeat things a bunch of times anyway, is extremely simple, and certainly, you know, is not even a sort of technique that belongs to conventional computing, but rather to, you know, even such things as electronics, building radios and what have you. So the way I would phrase it is like this: we'll deliberately make the errors worse. So the idea is captured by this diagram here. Along the horizontal axis, we have the error rate in our physical machine. And I'll say a bit about how you could vary it, but certainly you can't get it below a certain number. That's simply the best that you can do. So let's say this error level epsilon is just the lowest level of errors you can achieve in your physical device. Now, as you vary that error rate, any observable quantity associated with the output of your machine is going to vary as well. And as I mentioned, these observables, these expected values, are the things we're after. If we could turn the error rate down to 0, we would get the true observable quantity that we need in order to do a perfect variational algorithm. But we can't, we're here. So naively, you would just take this number instead of the ideal number, and you would just have to hope it was close enough that your procedure still works. But less naively, what you might do is indeed, of course, you do want this. This is your best quality output, but you boost the error rate to a higher level of error, sample again to find out what the expected value is now for this other machine, this machine that has more noise, and you attempt to extrapolate in some way in order to see what the observable would be, what's your best guess for the observable if you could achieve 0 error rate. So, and of course, the nearer you are to having no errors, so the more your extrapolation is likely to give you a good outcome. This is sort of captured in this cartoon by seeing that if we have too much error, then so we try to extrapolate from these 2 points, we would actually end up with a worse estimate. But as we converge towards lower error rates, we see that this should work because the observable quantity is always going to be a continuous function of your error level. There are other remarks to make. The only one I will make right now is that when you do this, when you boost the errors in the laboratory, it's important to do it in such a way that the nature of the errors, the error model, is the same, but the severity of the errors increases. If, for example, you just introduced a whole bunch of new error that previously was not in the device, then that would not be meaningful for extrapolation and it wouldn't work. So this is, we had a play with this. Let me skip through a couple of slides to this one. But it's now been used in many, this I think was the first really meaty experiment to use this kind of extrapolation process, which was, I should say, was almost the same time sort of proposed by this IBM team. And they were able to show that by doing this extrapolation, a device that previously wasn't able to come up with energy eigenstates at a level of precision that would be useful to chemists now could do so. Of course, it was a small device, so it was an answer that we could get by other means anyway. But it can be this very, very simple idea of extrapolation can be very, very meaningful. I'm going to skip over, it's a shame because it's a beautiful mathematical technique, someone can ask me about it, but I'm going to skip over a few slides here just to catch up on time and pause on this one that shows what happens as we increase the number of qubits and we try to use these error mitigation techniques. On the vertical axis is a multiplicative number. So this is how many times more you're going to have to sample a bunch of times anyway, but how many times more do you have to sample if you're trying to overcome errors by essentially clever kinds of repetition? And if you look over on the right, that's kind of a tough algorithm that's very dense, fully parallel. We find that as the number of qubits goes up, the multiplicative factor in how many more samples you're going to have to do becomes completely untenable. Let's say 10 to the 9. I don't think you can reasonably take a task that already needed a lot of sampling and times it by 10 to the 9 and still have a doable thing. And that's already just for 70 or 80 qubits. However, it's very, very sensitive, of course, to what is the inherent error rate. And if we assumed an error rate 10 times lower than current state of the art, then in fact, this does remain tractable even out to perhaps 100, 200 qubits. So error mitigation, there's hugely more to say about it, but it's certainly a poor man's kind of fault tolerance, but it can help by reducing or even removing errors at the cost of huge amounts of repetition. I'm going to skip through these one-sliders because I don't have time, but I do want to pause on this. But I did promise to assess whether or not variational algorithms with these kind of ideas in mind, these techniques, are actually going to be able to do something that's beyond conventional supercomputers that we care about. So a student of mine, supported by Quantum Motion, the company, took a look at this question with a resource analysis. He thought about the Hubbard model as being a sort of interesting thing that certainly relevant to theoretical physicists and that can be involved in other calculations, and was perhaps a low-hanging fruit in the sense that we might hope we'd be able to do this. He considered a 5x5 grid of sites as something that is somewhat beyond the classical capabilities that we anticipate for the next couple of years. and thought about what a quantum computer would need in order to find the ground state of this system using variational techniques. Here's how his analysis went. I encourage you to read the paper, but here are some numbers. He estimated that with a good variational algorithm, he might only need 100 overall steps to go from the initial state to a satisfactory approximation to the ground state. He estimated that the circuit necessary to determine the energy gradients, and I could say more about why this has to be so high, actually needed a large number of repetitions of the circuit, 10 to the 7. And then the error mitigation that you would need in order to make those numbers good enough to be able to be used, another factor of 20. So we're up to nearly 10 to the 9 circuit executions at this stage. And that within each of those circuit executions, you would need thousands of gates, but they could be run in parallel. So you would need something less than 1,000 gate sort of sets of gates in terms of how many time steps. And when he factored all this together, together with the speed that you might expect from a superconducting or silicon-based device, he ended up with 170 days to calculate this. And this, I emphasize, is really an entry-level problem in terms of what you would hope your quantum computer could do for you. So that is disappointing. If even this task takes 170 days, then we might imagine that the task we're really after, like solving chemistry problems for more rapid drug discovery and so on, would be really infeasible unless we have some very profound further advances. Of course, such advances are always possible. But there is another thought, which is to reduce that to a more tractable number. You could exploit the fact that what we're doing is fully parallelizable. We're sampling circuits, so why not have a whole bunch of independent quantum computers if you can make them small enough? They don't talk to each other in a quantum way. They just are all busily sampling the same or related problems furiously. And so if you have a technology that can build a very large number of qubits but can't yet connect them all up, then you have a scenario where you have islands of connected qubits, and that is very useful for NISQ. If you have 1,000 islands, your approach will go 1,000 times faster, and 170 days becomes an hour or two. So that is, we call that multi-core NISQ because as silicon researchers, we're very interested because indeed our structures will be very, very small and there's no reason not to replicate them on a chip. Now I'm going to skip over my bit about how we simulate stuff. I can answer a question on that, but I do want to get all the way to the end. So let's, in the last couple of minutes, if NISQ is so hard and if it does seem pretty tough to extract real value in the presence of noise, how hard? Let's look again at fault tolerance. So we have the surface code. It's very beautiful code, has very low demands on what we should make our qubits do. They only need to talk to their nearest neighbors. In fact, by checking the parity, which is how surface codes work, you not only defend yourself from errors, you actually can perform the calculation itself by enforcing or not enforcing parity checks between logical qubits, a very beautiful observation, which is called lattice surgery. So that all seems very encouraging. And of course, the primary point of all fault-tolerant schemes is that there is a threshold, a number, and as soon as your errors get well below that number, you're done. You no longer have to keep going back to the laboratory and saying, I'm going to need you to reduce the physical error rate, because instead you can scale, and not in a horrific way, in an efficient way, you can scale the hardware to crush down the logical error rate. So these, again, are all the desirable features. Now, the revelation here is that architecturally, fault tolerance is easier than NISQ, because what you're looking at is a structure where each qubit only needs to perform one of maybe one or two tasks over and over and over again. There is no altering the circuit to now update the parameters. There is no need to put in fancy circuits that represent an encoding of the problem. You just have a substrate, a very simple fabric on which you do the same thing over and over and over again at each location. The problem is just the number of qubits that we need. I'll skip this one. And so here, finally, is an example of a blueprint, I mean, a rather schematic blueprint, but still, that Quantum Motion has for one of its ideas for fault-tolerant quantum computing in silicon. That you can see a lot of black dots and white dots. The black dots are data qubits, and the white dots are measurement systems. And so this is a small piece of surface code that we see here, 4 by 5 chunk of it, which would already be a fault-tolerant qubit, But of course, we'd need it to be more like 30 by 30 to be a really robust fault-tolerant one. If we zoom in a bit, we see that it's just this structure repeating over and over again across the entire device. So just to say that one more time, the entire surface of a silicon chip would just be covered in this repeating structure. And that is all you need, which is very, very appealing in terms of the simplicity of the thing. So the layout is designed to support the surface code and only that, but that's all you need. Crucially, what's novel about this design, and I encourage you to go and read the paper here if you're interested, is that the problems which the code finds it hard to deal with, which are called leakage and loss problems, whereby qubits can even cease to exist, are handled at the architectural level. We build into a stabilizer cycle, the measurement of the parity of 4 qubits, a refresh process, which essentially sorts out these kinds of error, which are tough for the code, at in terms of the hardware itself, canceling it out. And then so the architecture maps those difficult kinds of errors to essentially a depolarized qubit, which the code can handle, and then we obtain attractive thresholds that we, of the order of 1%, which is what we want, because we think we can get there in terms of the hardware. So we estimate a sub-micron pitch in terms of how far it is from one black dot to the next. And that, if you sort of do the arithmetic for a chip that's a couple of centimeters on a side, you end up with hundreds of millions, perhaps as many as 1 billion physical qubits per chip. And so there, I want to leave you with this sort of provocative thought, which is why silicon is exciting, even though it's much further behind in terms of how many qubits people have demonstrated working together. We have our superconducting qubit vision, where we have mega dill fridges that are 6 foot wide and contain maybe up to 1 million qubits, and then we network them together in, I suppose, a 30 by 30 grid if we wanted 1 billion qubits. So that is an entire floor of a building, if not a building, dedicated to the computer. But in silicon, if indeed we can achieve the gate fidelities we need, then we have that device, that entire floor of a building or building on a single chip. And, so how would you like your 1 billion qubits? If both are possible, I certainly would prefer mine in the form on the right. Of course, these are just images of a chip and a server center, just to sort of give us something for our imaginations. So with that, I'd like to wrap up, and I'll just say one more thing, which is that the company Quantum Motion that I've mentioned a few times is hiring people. So, and also working with consultants, so people, multiple levels of seniority. We really just want to talk to people. So do drop me a line or drop a line over at jobs, and we will get back to you if you find any of that stuff interesting. And at that point, I think I'm over time by a couple of minutes, so I better stop.
Thank you very much, Simon. And I'll open the floor for questions. I can start with a provocative question. I don't know how really provocative, but so what's the the biggest or largest number of silicon qubits that people have demonstrated to kind of do something?
Yeah. So the answer is a few years ago. Well, it of course depends on exactly how you phrase the question, right? Because you can have a sort of an electron oscillating between 2 dots, and you can call that 2 qubits or not. But a few years ago, I would say the answer is 1. So you would have 1 rather nice, well-behaved, long-lived qubit in silicon. But now I would say, from the last couple of years, it's clear that the answer is 2. So, but that's a rather profound difference, because the difference between 1 and 2 is, the second most profound thing after 0 and 1. So what one can do there is exhibit a entangling, entirely appropriate gate on which you can make it either a sort of square root or swap based or a CNOT gate, but a suitable gate for quantum algorithms has been achieved at the 98% fidelity level. Now, 98% is not good enough and is lower than the sort of numbers that Google have, which are in excess of 99%. But the threshold for fault-tolerant quantum computing is at about the 99% level, depending very much on the nature of your noise. So I would say that a factor of 5 increase in or reduction in the noise level would already be enough, but we could potentially be able to think about now building these fault-tolerant quantum computing layouts. So we've only got a 2-qubit gate between 2 qubits. I haven't got a device that's sort of 10 qubits in which this 2-qubit gate can be switched on and off. But of course, the field is racing towards that. The fact that a 2-qubit gate is possible at all, and with a pretty good fidelity as an entry-level offering in the field, is extremely encouraging. But I mean, if I can just say one more thing, because I can see, you know, it's of course the right question to ask when other people are doing 50 qubits and rival companies are projecting 1,000 qubits in 3 years' time. I would say the following. I'm not here to tell you that it's definitely possible to do better than threshold operations in silicon with spin qubits. That is an unknown point. I would say I'm optimistic about it. But what I will say is that given that it looks like it's probably possible to do that in silicon devices that are essentially the same as the chips that work in your iPhone, then it's absolutely the right thing to have a really hard look at that. Because if you can get gates to work between these components, which essentially would be manufactured by the same fabs, the same foundries that we use for phones, then that's a profound game changer in terms of how rapidly we can get to the fault-tolerant era. And more than that, the sort of democratization of the whole thing. If each quantum computer that's really able to do big problems fills a building and costs £1 billion, then you're not going to be using it as an end user, even in the cloud. If it's possible to have better AI, you know, I'm just making up a random thing, using a quantum computer to augment classical devices, you're still not going to be using a slice of $1 billion machine any more than the things you want to do get to run on the Oak Ridge, you know, supercomputing facility right now. But if quantum computers of that kind of scale can fit on a chip, then you can still have a server center size facility, but now it's got thousands and thousands of quantum computers in it. And now you can use it as a sort of end user. You don't have to be a mega company or the military in order to access a quantum computer. It can really be much more impactful. So for those reasons, I think, you know, if there's any chance, and I think there's a good chance, excellent chance, that silicon can do this, we need to investigate it. And if the answer turns out to be no, then we still have these very nice alternatives that are, you know, much more bulky in the form of superconducting and other approaches.
What about quantum dots based on like gallium arsenide, or do you think they don't have?
Yeah, I mean, it's too early. Yeah, right. So, okay. So a possible scenario that we can't rule out right now is that for reasons, silicon turns out not to be able to support qubits of the quality that we need, but other semiconductor systems that still, you know, are closely related are able to do it. And so you could go into the pros and cons. I think actually the groups that I'm familiar with, not everybody of course shares their plans with us, but the groups I'm familiar with are tending to go in the silicon direction, if anything. But so that would certainly be another scenario. And then you would not be in this sort of ideal scenario of being foundry compatible, but you would still be able to work at that kind of very attractive scale. But you know, so that's the sort of basic pitch on the company. So that's, and this is one of a range of ideas. It's important to have these blueprints so that we can work out where we are, even if we're only at sort of the early stage of the roadmap towards coming towards this device. But this little guy here this is kind of the crucial thing. This is a jigsaw piece in the world's most boring jigsaw, because it's just the same jigsaw piece over and over and over again, you know, for thousands of pieces in each direction. So if this jigsaw piece can be demonstrated, and in a way where you're accessing everything, not in the horizontal plane, but because that you're going to use that up with other jigsaw pieces, then, you know, you actually have achieved your proof of principle. Are there other questions? That doesn't have to be about the silicon thing. That was just my provocative point to end on.
Simon, I have a question. Can you hear me?
Yep.
So it seems you have these very interesting ideas about NISQ and very dramatic conclusion. My question is that, have you talked to the chemists that do these simulations? Because for the years I've been in this community, we always seem to be talking about how quantum computers and simulators will be able to solve all these problems which are unsolvable. And then sometimes when you actually hear from some of these people that work on doing the problems, it seems like many of them don't seem to even think that they need it, that they need this ability.
Right. Well, that's a fair point. So there are chemists who have the view that they don't need quantum computers because there's still a lot of road ahead of them in terms of improving their algorithms together with anticipated further improvements in conventional hardware. So that is a view. I thought you were going to go in a slightly different direction. I mean, talking to chemists to make sure that we're using all their best tricks is certainly something that one must do, right? So there's a guy who's just joined Oxford from Bristol, a guy called David Chu, who is a rare beast, which is a quantum chemist who's very interested in and involved in and knowledgeable about how quantum computers work. So yes, we do talk to chemists, and I'm always looking for opportunities to talk to more chemists. And we do also try and be aware of the full literature. In fact, my group has a review paper along with Alan Aspuru-Guzik as a co-author, which is quantum computational chemistry that sort of represents everything we know about the overlap between chemistry and quantum chemistry techniques and quantum computers. But even so, my own view on whether NISQ is going to help us crack those kind of problems is, I'm an optimist, so I would say yeah, but it wouldn't surprise me if the answer is no, because it's very tough. You're asking to get a complex task accomplished with components of your machine that are constantly going wrong at a significant rate. And you want to outcompete an extremely mature technology where, vast numbers of trillions of bits can be harnessed in conventional algorithms and do so in an essentially completely error-free way. So it's a big ask, but it's a fascinating thing to think about even in its own right.
I have one more question, which might be is less science oriented. Did you get investors to invest in your company using the word explore?
Well, I think develop is a better word for investors, but I think that silicon has reached the point that many approaches are reaching where the correct way to pursue it is not in a purely academic way, because you need to be doing deals with foundries that can provide chips. You need to be bringing online, moreover, types of expertise that would not normally be in a physics or engineering or materials department or computer science department. You need people who are exactly the same sort of people that get recruited into the likes of Intel and NVIDIA and so on. And so the need to have this sort of heterogeneous team and to have salaries that look reasonable, if not, directly competitive with what you might get from working with one of these titans, means that your challenge has now moved into the regime where the best way to address that challenge is with a sort of agile company, and rather than an academic group, even if it's very well funded by sort of governments and so on. And I think, you have to look around, but there are investors who are inspired by the opportunity and are indeed, keen to get involved. I mean, the answer is obviously yes, right? Because we got our investment. But of course, it's not for all investors. There's a significant high risk, high return element to this kind of thing.
Thanks.
Sure.
Other questions?
I have more of a technical question, I guess. You compared different algorithms in terms of the number of iterations they need to converge. I wonder if that takes into account like measurement noise from doing a finite number of measurements. I mean, how do the different algorithms compare in terms of that?
Yeah, let me see if I can go back to the one. Nope, it's further back where I was doing that. This kind of thing, for example. In fact, if I remember.
Yeah, exactly.
So here, it's a very, it's a very good question, right? So we're comparing two quite different approaches, one of which is a sort of a steady gradient descent method, okay, natural gradient, bit fancy, but versus one that does a different way of inferring its way forward. And it's important to compare things in a fair way. So I think we're sort of I wouldn't say we've completely finished our comparison of those things, because there's a number of different ways you might ask it. But the specific question you asked about how many times you have to sample to get things to an adequate precision is in consideration in this paper. The kind of thing that's not thoroughly looked at in the paper yet is stuff around the impact of errors. So I wouldn't expect that to differentiate the two models severely, but also subtle features about how much you can squeeze out of conventional gradient descent if you allow yourself to not do a sort of smooth trajectory, but instead take a daring long step in the direction that you've computed a gradient that you think is the best direction to go in. Maybe you've used natural gradient to do a smart choice. Do you take a small step along there so that you know that you're following a promising trajectory, or do you take a longer one when in fact you will do something adaptive, right? So it is true that there may be some evolution of these curves as you use smarter and smarter techniques to try and squeeze the best performance out of each of them. But my current thinking is that it is going to be the go-to method in certain circumstances, because you just get such a nice return. The important point here is actually that to infer the entire surface, you only need a surprisingly small number of sampling around here. So in a sense, why wouldn't you do it, right? If you can infer the entire surface with only something like 4 times the effort that it would take to get the gradient, then go for it, right? But it's certainly still, we haven't, this is a complete project in the sense that we've written it up and put it on the archive. I'm going to put it into review, but we're still furiously asking questions about it, and sort of, I hope that we'd have a lot more to say in a year's time, because we're currently quite excited about the idea.
Thank you very much.
Sure.
Right. Other questions?
Maybe I can comment as a chemist who plays with Hubbard models. Doing a 5x5 Hubbard model directly by brute force exact diagonalization is indeed something that we can't do even on a supercomputer.
Yeah.
We have a huge number of approximate algorithms.
Yeah.
And actually what you're showing is also an approximate algorithm. It's essentially variational.
Yes, I'm trying to find my slide while you talk. I agree with everything you said so far.
So the interesting thing to me is, and maybe I missed this, maybe you discussed it, but can you really show that this is for instance, a much more powerful variational ansatz than anything that I can do classically? Can you see that you can get better precision than the best of breed algorithms that are available now?
That's certainly a good question. I don't think that, I'm trying to remember that. So, okay, to be clear about what goes on in this paper, Sai takes an approach that had previously been discussed in previous papers about how you might use a variational approach to solve this, and he sort of fleshes it out in a lot of detail and adapts it somewhat in order to be able to do this careful and full resource analysis. Now, the kind of question that you would want to ask is, are the ansatz circuits that Sai is using here able to get closer to the energy that you want than the kind of approximation techniques that you would use anyway if you were just given access to a meaty computer and classical techniques?
Yeah.
And how confident can we be that the ansatz circuits he's assuming here are good enough? And I don't know the answer to that, as in how confident we are. But I think I can turn it around and say, if the ansatz circuits he used here were significantly smaller, more shallow, then I think we wouldn't expect a performance that can potentially outperform conventional techniques. Because the aim here is to come up with a number that it essentially lower bounds the runtime on the quantum machine before, so we're looking at a low-hanging fruit. We're making various optimistic assumptions about the error rate. And in a way, we're also making a somewhat optimistic assumption by saying that the ansatz circuit is deep enough that with the right parameters, it can outperform classical approximation techniques. And even with all those, fairly optimistic assumptions, we still end up with 170 days to compute the thing. And I think you can push back on multiple aspects of these optimistic assumptions, and that will, of course, make this number worse. So that's not a full answer to your question, but it's sort of from the point of view of.
Well, I'm saying that the fleshing out what it means to compute the thing, right? What you're actually trying to accomplish and to what accuracy matters.
Yep.
Because it's very possible that I can run, a pretty old auxiliary field Monte Carlo algorithm and get a better result on a laptop. I'm just not sure what you're actually doing.
Right, exactly. But you see, that plays into my narrative, if I may say so, because if that's true, then I either need to deepen the ansatz or I need to increase the problem to maybe a 10 by 10 array. And then, I assume that, depending on how your approximation techniques scale, then that starts to give you a headache. So at least this problem scales only linearly in the number of sites. So, if it is true.
Sure. I mean, we all understand that eventually quantum computers.
Exactly.
Right.
So, I mean, let's say that the case that Sai's looked at here actually can't outperform a laptop or at any rate a sort of a small supercomputer. Then we would have to beef up the problem in some way. So it would either need a deeper ansatz, or we'd have to attempt a more ambitious size of array, and so on. And then the number of days to compute the answer will be more than 170. So the real message that I wanted to convey from this is that when we try and do these kind of analyses, albeit that we have to make some assumptions, approximations, and so on, we end up with in this example, we have ended up with a number that isn't, a million years or 5 seconds. It's in fact a number that's just rather disappointing in that it's unlikely anyone would actually use their quantum computer for 170 days to merely compute what's still rather an artificial problem, right? So in fact, this is a no on whether or not we can do the Hubbard model with the kind of hardware that's presumed in this paper, unless we can cheaply produce a huge number of them, in which case the answer is maybe. So it's a sobering, I want this to be a sort of sobering note. Further advances could clearly bring this number down, but then you only need one thing to go wrong, like your error rate is not actually as good as the one that Sai assumes, and then that will cost you hugely in this term here. And so we're very much in the maybe, maybe not domain about whether NISQ can do these useful problems. And it's not even the problem you want to do, right? You want to actually solve an interesting molecule, perhaps, more directly than sort of studying.
I mean, we'd be happy with that, right?
You'd be happy with that.
Questions about Hubbard models. But,
okay, all right. Yeah. Well, I mean,
nevertheless, right? So when you talk about the parallelized algorithm, right?
Yeah.
If I have many copies of my quantum computer somehow,
yeah.
Even though I think a quantum computer is quite expensive, unless you guys manage to do it in silicon.
Yeah.
Then do we have perfect parallelization, right? If I have 170 of them, I can do it in one day.
Exactly that. Yeah, perfect parallelization, because the whole thing here, sorry to keep flipping backwards and forwards, is a bunch of stuff that has to happen. It's sampling repetitions, and in particular, this big number here is just the cost of repeating a circuit over and over and over again in order to extract a number to several decimal places and then extract a whole bunch of parameters that way. So that's completely, this one here, for example, is completely parallelizable. And if you had 2.5 times 10 to the 7 quantum computers, you could do it in one step. So, that at least is somewhat encouraging. So if it becomes
that's extremely hopeful, actually, right?
Yeah, right.
Making more quantum computers is probably easier than making better ones.
I couldn't agree more. I mean, so 10 to the 7 is a big ask, but if you can put 1,000 on a chip and you put 30 chips on a wafer, then suddenly you're starting to hack away at these numbers. And even if we then, as you say, have to consider a larger array or a deeper ansatz in order to have post-classical performance, we may still be in business. And I'm pleased to hear you say that if someone had a black box that is a Hubbard solver with sort of arrays of, I don't know, 10 by 10 or something, that you would be excited to use such a device.
Well, what I said is that it depends, right?
Okay. Yeah. Of course, it depends on whether it does
better.
Depends
what you mean by a Hubbard solver.
Yeah. Well, okay. But I mean, there we are. So that is the embarrassingly easy parallelizability of NISQ where one doesn't need to have a quantum link between the processes is one of the reasons for optimism. Not if your quantum computer is a huge bulky thing, but if it is one of several approaches, and I would say silicon is the most exciting, where your 100 quantum qubit, or in this case 50 qubit quantum computer is a teeny weeny, invisible to the human eye speck on the surface of a chip, then that's rather exciting in terms of just stamping out a whole bunch of them.
Certainly is.
All right, thank you.
Thank you.
So are there any further questions? With lots of questions. I just got a quick question about the, about the part where you were trying to get the kind of higher energy states. So somehow.
Oh yeah. Yeah, that's one of the things that I zoomed through.
Right. So I mean, we don't necessarily have to go into technical details. I just want to understand. So you're saying you're able to kind of perfectly project out states just without reverting to a non-local Hamiltonian, or is it just some sort of approximate projection?
Okay, so what we can do is, so leaving aside the difficulty of, so if you had a machine that you can just give it any Hamiltonian and it gives you a low-lying state in that Hamiltonian in some kind of representation, right? I mean, even that would be, well, what does that mean exactly, right? Because how is it giving you that state in a way that you can actually write down? It could give you the state itself, but anyway, you might say, well, now I'll consider a Hamiltonian, which is something like the old Hamiltonian plus some big number times a projector onto that state. And that's now a new Hamiltonian that hates the state you found previously, and that certainly won't find it again. And then you'll find a new low-lying state, and you'll now define a Hamiltonian that's minus both those projectors, and now it hates both of those ones. But that's not, what does that even mean? You would need the device to be able to describe it to you in order for you to even write down the Hamiltonian that represents that. But of course, what you do know is, you know, the parameter configuration that represented the states that you previously found. So in fact, to be quite honest with you, I'd have to refresh my memory because this one was a while back in terms of the exact tricks in it. But essentially, by looking at the fact that you've got this parameterized circuit, you previously found a set of parameters that represents a low-lying state of the system, you can then repeat the process where you're essentially penalizing that configuration in such a way that you won't find that configuration again. So it becomes a problem for the classical algorithm and not really a quantum problem anymore to forbid rediscovering that state. And maybe I'll just leave it at that because otherwise I'm going to say something that's incorrect.
Yeah, that was helpful. Thank you.
All right. Well, sorry that I had to skip through some slides, but I very much enjoyed receiving questions during the presentation.
Thank you very much, Simon, for this talk. It was wonderful. Yeah, and hopefully I will keep in touch in the future.
Yeah, I hope so. All right. I would love to visit when, you know, at some future scenario that's some unknown distance in the future, but I don't think I've ever had the opportunity, so I'd love to. Thank you very much for your attention.
Thank you very much, Sam. Bye-bye.
Bye-bye.
Thank you.